Hey, what's up, guys? This is Sheng here again. So this time, LeetCode number 1900, almost 2000. So the earliest and the latest rounds where players complete. Okay, so this time we have a tournament where N players are practicing, and the players are standing in a single row and are numbered from 1 to N. Okay, and based on their initial standing position, right? So the tournament consists of multiple rounds, starting from round 1. So in each round, basically, the first player will be played against the last player. And the winner advances to the next round. Okay. And when the number of players is odd, basically the remaining players, right? So the players right in the middle will automatically advance to the next round, right? So for example, we have this kind of 1, 2, 4, 6. 1, 2, 4, 6, 7, right? So at the first round, the first player will play against this one, and then this two will be played against each other, and the four will be advanced automatically to the next round. So, and after each round is over, right, the winners are lined back in the row based on their original order. So basically, once 1-7 is finished, basically either one of them can be a winner, right? So let's say, for example, if 7 wins, right? So the 7 stays here, but one is eliminated. So for example, when 2 and 6, let's say 2 wins and 6 is eliminated. Now, after first round, we could have like 2, 4, 7, and then the next round, this everything happens again, right? Basically, 2 and 7 will be placed against each other, and 4 will be advanced, right? Okay, so that's the basic rule of the tournament, and then you're also given like two players index, first player and second player. Those two players are the best in the tournament, and they can win against any other player before they compete each other. Right. So which means that let's say in this case, if the 2 and 7 are the first and second player here, so anyone who play against them will be a loser, right? So basically, whenever uh, 2 and 7 compete with other like players, they will advance to the next round, and the game stops when the 2 and 7 plays against each other, because that's the time we will decide who is the final winner, right? Because we know they are the best two. We just need to wait for them to compete with each other. Cool. Then as you guys can see, right, we could have like different results, right, by the result of each round. And so here, so when whenever two players are not either the first or second player play against each other, we can choose who will be the winner, because anything can possible. Basically, uh, let's say one plays against 6, right? So either one can win or 6 can win. So both can happen. And our task is to find the earliest possible round and the latest possible round that these two players will play against each other among all these kind of different scenarios, right? So that's basically the idea, okay? And so, for example, we have 11 players, right? And then the best two players are 2 and 4. So the answer is 3 and 4, which means that so the first player and the second player can compete with each other as early as the third round and as late as the fourth round, right? So here it gives you some scenarios here. This could be just one of the possible scenarios. There could be many, right? And so there's a constraints, right? So it's 28. I think every time when you guys see this kind of n is smaller enough, like 30 under 30, it's a strong signal that you may consider using the bit mask, right? Where the in this problem, basically we have a bit mask. So the bit mask, and we could have like several players here, right? So at the beginning, everything is one, right? Basically, in this case, I use one to represent this player still exists. And every time, right, based on this bit mask, we need to explore all the possible next bit mask, right? Which in this case, these two can be either 1 or 0, right? Basically, either this one can be 0 or this one can be 0, right? Let's ignore the best two players, right? Let's just explore the normal case, right? And then by the time we have played, we have enumerate all the bit mask for the current one, then we know, okay, so this current round is finished, and we can increase that round by 1, right? We can plus 1 with that round. So as you guys can see, given like a bit mask, right, the minimum and the maximum rounds for those two players to play against each other is fixed. So it means we can DP on this mask, right? But the difficulty for this problem, and so we DP on this mask, and whenever during our like process here, whenever we find, okay, so we see like the player 1 is playing with against player 2, and then that's when we need to return the final result. It could be return either 0 or 1, right? I think it should be 1. Then the problem comes down to how can we, I mean, given like a mask, like current mask, how can we get to the next state of mask, right? Like I said, it could be anything, right? So let's for example, this is the first the initial state, and from this state we need to basically find the next possible state, right? Like I said, this one could be 0 or 1. This two can also be 0, right? So this could be 1, this could be 1. As you guys can see, so at each of the state, right? So I mean, half of the size we have to somehow explore everything for this bit mask. But the issue for this approach is that, I mean, it's not an issue. At least you can do it. Basically, one way of doing this is that you at each of the state you also maintain like another left and right along with the mask, right? So you also maintain the L and right, which means that, okay, we're currently processing at this location, right? So for example, this is L and this is R, right? And every time at each of the state, we'll check, okay, so if the L is 0, then it means that okay, so this player has been eliminated. Then we simply move L to the right. Same thing for the right, right? So if R is eliminated, we'll move to the left. So that's the two scenarios, and then whenever we have, and then when do we move to the next round? That's when the L is equal to R. Actually, it's L L is either equal or greater than R. That's when we move to the next round. Next round. So this is when we need to do a plus 1, right? So why L is greater could be greater than L, because if this thing is even, right? So at the end, L is here and R is here, right? So whenever we finish this one, if we do L plus 1 and then R minus 1, at this moment R is greater than 1, right? So if it's odd case, then L will be equal to R. That's why we do this thing here. and that's one way to solve this one. But unfortunately, if we do it in this way, as you guys can see, other than the mask here, we'll also be maintaining the left and right, right? So if we do a DP, right? If we do this, right? So if we do this one, basically this L and R will be adding another two-dimensional to this mask here. And unfortunately, if we do it in this way, Python will TLE, but C++ can pass. So I already tried both. No, so that's unfortunate for Python again. So which means that even though this approach might work, but we cannot pass all test case in Python. So which means we cannot use mask here, the beat mask. Oh, and maybe one more thing. So back to this, the first approach here, whenever we move to the next round, right? So whenever we move to the next round, then we'll be moving this L and the right into the n0 and n-1, right? Because we don't know, because after the round is finished, we have to start from here and here to check to play the next round, right? Even though there's some like zeros along the way, we still need to pass them. Here, as you guys can see, still this also like add a little bit more complexity to it, because we will be processing a zero eliminated players multiple times. Basically, how many rounds, right? Each round we play, we will recheck that eliminated player again. So, and what's going to be another solution, right? I mean, this is like a common alternative. If we don't use mask, then we simply just need to maintain the actual players, right? So instead of memorize this bit mask, so we will be memorizing the players. So these players will be the remaining players, right? So the remaining players will be the index, it's a tuple basically. So this one will be adding like a little more space complexity, but this one will decrease the time complexity quite a lot, because we will not needing this L and N right? And if we maintaining like a list, we can use like a Python utility tool. It's called product to help us in one a DP function. We can use a product to quickly help us find all the possible combinations, right, for the next state. And that's what we're going to do for this problem. Okay, so let's start coding then. All right, and all right, so this is going to be a DP, right? So I call it players. So the players are the players who are still in the tournament. Are you cache.none, right? And like I said, so in the end, we simply return the DP of tuple, right? So we convert this all the players into a tuple, and this one it will return the minimum and the maximum round until top players play against each other. So that's this basically this is the result this DP is maintaining, right? So for each of the round, right? So we have n. We're gonna need this kind of players. That's gonna be the half players. And to use a product, so the way the product works is that we give like product a list of of a list, and then the product function basically will do a we'll pick each one from each of the lists, and then we'll try to multiply, right, with find like a combination for each of the list. And it's essentially like a Cartesian product, where that is equivalent to a nested for loop, right? Basically, if we have three lists, right? List 1, list 2, and the list 3. So for each of the lists, we're gonna have like a for loop. So for this one, we have a for loop, and this one is a for loop. This one is a for loop, right? So if we have 10 lists, we're gonna have like a 10 for loop here, right? So each one will loop through everything inside here. That's how we get the Cartesian product, right? And that's exactly what we need. So which means that, if we want to use the product, we need to find all the pairs, right? So in order to find the pairs, we just do a for loop here, gonna be a n, we do a half, right? So that's why we have player 1 is gonna be a players of I, and then player 2 will be the players of -1 minus I, right? And actually the base case can be checked inside the for loop here, where if the P1 equals to the first player, right? Too long, F and S, and P2 equals to the second player, that's we will stop the tournament. So when we stop, we simply return 1 and 1, right? Because I think the round starts from 1, right? So basically at the very beginning, it's around 1. That's why we instead of returning 0, we return 1. This is the base case, right? Because at here, the minimum and the maximum, they're both 1. Otherwise, right? So otherwise we will find the pairs. Okay, so this is a pair. And so here's the trick here, because if we do a product, so all the combinations will be generated. So which means that the if any of the player is a top players, then we cannot put them into the pair, because if we put everything into the pairs, when we use the product, there could so the scenario that top players will also got eliminated will be generated as well. That's why when we insert a pair, we only insert pairs for the players that are not the top players. Basically, if the P1 not in FS and P2 not in FS, right? Then we add the pairs. Pairs dot append P1 and P2, right? So then how about the remainings, right? So the remainings will be like this. So the remainings will also always be there. That's why we have a remainings. Gonna be the FS, right? But there's a special case, where the person right in the middle will automatically advance to the next round, right? So we can do something like this. Basically, if this thing, we return this one if it's even, right? Else we return the tuple of else we return this fs and players of n divided by 2, right? But there's a bug here, Why is that? Because this one could be either f or s, right? Because let's say we have this 2 here, this is f, this is s. This is also possible, right? That's why, you know, in this case, we cannot blindly just add this one to here. You know, we can simply do a trick here. We can convert. How can we eliminate the duplicate, right? We can simply convert this one into a set. So after doing a set, so the duplicate will be removed, and then we convert it back to the tuple, because set is a not tuple. And the reason we need a tuple is because the result for the product is a tuple. And in order for us to be able to append the remains to the product result, we have to use tuple. Okay, so now we have the remains here, right? And now we can finally use a product and do this pairs, right? So for those who don't know, so what does star pairs mean? So basically, you know, pairs is like so pairs is it's a list of lists, right? And the star pairs, basically it will unpack this pairs into a multiple list like this. Because currently, you know, the pairs is like this, right? So the pairs, let's say we have 3 pairs in it. That's how the pairs works. But the product needs the parameter for product is a list. It's a list of lists that we need. Instead of this one, we need what's inside. That's why we use a star pair, which will give us this part. Okay, and this one we're going to be a pair 1 2 no 1 7 2 6, right, and 3 3 5, something like this, right? And what the product does is that basically it will pick, it will randomly pick, it will pick one from each of the pairs, right? Basically you'll pick one and then pick one from here, and then you'll pick this one, this second one here. Basically it will try all the combinations to pick each one of them from each of the list, and that's exactly what we need, right, for our case. That basically this is the simulation for all the possible next round results, or the current round results. So we have a result. It's going to be a DP of so the next round will be so first we're gonna do this, right? Remains, we add. So first we add this remains, because this is the remainings we need to be taken care of, right? And then we need to and remember, so this one is what? It's a list, right? It's a list, and the sequence could be different. But remember, we want to keep these players always sorted from the smallest to the biggest. That's why we can use this kind of like 2-pointer technique to find the correct the competence, right? The players that can play against each other. If we don't sort, you know, we may end up having two incorrect players to play against each other, because product will be picking anyone, right? You know, like I said, we have 1 7, right? 2 6, and then 3 3 5. You know, we could have picked 7s, and then we have 7 and 2 and 5, something like this, right? So in this case, you know, so actually it should be 2 5 7, right? Which means that, you know, 2 should be placed against 7. But if we don't sort it, as you guys can see, if we use this for loop again, so actually 7 will be a play against 5, which is wrong, right? That's why we need to do a sorts. And after sorting, we also need to convert it back to the tuple, because that's the only way we can hash it, right? So we have tuple, and we do a sorted of next, right? So that's how we do it. So now we have a result, and it's time for us to maintain these two things. So we have a minimum, going to be a system dot max size max gonna be a min system dot max size again, right? So we have a minimum, because the minimum of result 0, and don't forget to do a +1, right? 1 + 1, right? So it's obvious, right? So +1 means that because we have already done one round, we need to increase the round number by 1, right? And then so we simply return the minimum and the max in the end, right? I mean, we can maintain two things at the same time because, you know, like I said, given the fixed players, the minimum and the max rounds until the top two players uh, to play against each other are fixed. So every time, as long as we have seen these players once, you know, then the minimum and max are already calculated. Then we don't have to revisit this state for either minimum or max scenario. And that's it. I think that's it. And this is the exactly the result we're looking for, right? So it asks us to return, yeah, two values here. So if I run it, okay, yeah. So the set needs a list. Oops. Arrow exception. This is weird. Let's see. Where did I do wrong? Oh, here. Oh, the base case. Oh, it should be F and S. Yeah. If this is wrong, we'll never be able to return. That's why we got a maximum recursion depth exception, right? So, all right. All right, cool. So if I submit, all right, cool. So it passed, right? And so that's it, right? I mean, it's not too complicated, but you know, the product and thing is a little bit tricky. You know, if you haven't used it many times before, it's a little bit tricky to use it. And so for the time complexity, um, so here, so we have a for loop here. Basically, the time complexity for this for loop will be the 2 to the times of half n, right? Half n here because we divide this n by half, okay? And basically we have two n divided by two pairs, and that's why when we do the products here, we'll have like this one, right? That's the time complexity for this one. And then for the state, right? So we have a players here. You know, we could have a different state because this one needs to multiply by the number of states here. So the states can be, I would say, you know, it's also in the range of 2 to the power of n here, you know. But actually, in reality, the total time complexity is much smaller than this one because, as you guys can see, the players will be decreasing every time, and this thing will also be decreasing, right, by half every time. And since we also have like this kind of two players, that who will always be winning, and we have some like base cases here. So in reality, you know, so even though it's like in the scale of 2 to the power of n time complexity, but in reality, this one is like smaller. I think it was smaller than 2 to the power of n because n is pretty big, like 28, right? I would say maybe it's things around 2 to the power of 20, maybe. something like that. It's just my guessing. I cannot figure out the exact number here. Yeah, I think that's pretty much I want to talk about for this problem. And yeah, and thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.